So welcome to the last part of lecture 17, where we've been talking about linear operators and attaching them to polynomials. Now, very interesting that there's actually a question we haven't really addressed. We've defined what an eigenvalue is, but we haven't actually justified that eigenvalues have to exist, right? So the question is, does a linear operator have to have an eigenvalue? And the answer is that you actually have to worry about which field you're playing with, right? So what we're going to prove is that if the field is the complex numbers, yes, you can always find an eigenvalue, but if the field is the real numbers, it may actually may not have an eigenvalue. And the interesting thing is to kind of get at the proof for the for the complex numbers, we actually are going to use a property of polynomials that we discussed when we talked about the chapter of polynomials. Okay, so I'll explain this in this last part of today's lecture. So let me make myself disappear. And here's kind of the big theorem we want to do in the next 5-10 minutes, is that if you look at a vector space over the complex numbers, then every linear operator has an eigenvalue. Okay, so let's kind of walk through our way through the proof. So let's assume that our vector space has positive dimension, and let T be the linear, any linear operator, and just take any vector inside of your vector space. Just take any vector as long as it's not 0. And then look at the vector, this collection of n+1 vectors that you get. So you take v, tv, t squared v, t cubed v. So you're just taking v and you're just plugging it in to t over and over again, and you're getting a list of n+1 vectors. Now, what we have is our vectors, and they are what we get are n+1 vectors, in an n-dimensional vector space, so they're linearly dependent. Okay, so there has to be a linear dependence relation among them, because you can't have n+1 linearly independent vectors in an n-dimensional vector space. Right, so remember what that means is that there exist numbers in our field such that we can write this as a0 times the vector v plus a1 times the vector tv plus a2 times the vector t squared v all the way up to an times tn times vn, and we can get a linear combination equaling to 0. And I want to point out, with not all of a1 up to an equaling to 0. Okay, and just want to point out why we can say this, right? And it's because if they all were 0, then we have that a0 times v is equal to 0, i.e. a0 is 0. But that's going to be a problem, right? Which forces v up to t and v to be linearly dependent, or sorry, not dependent, independent. That's the contradiction. Okay, so the key thing that we want is one of these numbers a1 to an has to be not 0. Okay, so there's one of the numbers a1, a2 up to an that's not 0. Okay, well now what we're going to do is we're going to use those exact same numbers and we're going to build ourselves a polynomial. Okay, so we're going to build ourselves the polynomial pz using those numbers. So a0 plus a1z plus a2z squared up to an times zn. And here's where we're using the fact that we have the complex numbers, right? By the fundamental theorem of algebra, we can factor this completely into linear forms, or into linear polynomials. So you can factor as the polynomial pz as some constant times z minus lambda 1, z minus lambda 2, up to z minus lambda m. And note that m is less than or equal to n, since we don't know if an is 0 or not, right? Since an may equal 0. We don't know what actually the degree of this polynomial is that we get, but we know that it can't be 0, right? Because that's the condition that we have here, that a1 through an is not 0. So this polynomial is not, it's not a degree 0 polynomial. So it can factor. And so what that means is we know that there's a linear combination among these vectors, and that's equal to 0, which is what we've written right here. But you can think of the 0 vector as the output that you get when you take v and you plug it into this linear operator right here. But this linear operator, right, this is the same thing as the linear operator that you get when you plug pt into the polynomial that I just had over here. Let's call this, I do have it right here. This is the same thing as that. But this is the exact same thing as the operator that you get by the factoring, right? So t minus lambda 1 I times t minus lambda 2 I all the way up to t minus lambda m I v. Okay, so we have some constant and then this linear operator that's been factored. Sometimes we've factored the linear operator into all of these other linear operators. So we step back and say, what I have is I'm taking this vector v and I'm plugging it into this linear operator, and my output is 0. So that means the vector v is in the null space of the thing on the left-hand side. But that means one of these operators has a property that it will take something that's not 0 and suddenly make it 0 at some point. So you would take v and you plug it into the first guy, okay, and you may or may not get 0. Okay, if you got 0, then like everything else from there would be 0. If not, you would plug it into the next guy and you would get 0 or not 0. And at some point you're going to get something that was non-0 suddenly giving you 0. So that implies that one of these operators must be not injective. Okay, right, and let me maybe add some more details. V is not equal to 0, but it is sent to 0. So one of these guys inside of here is 0, but when that happens, when t minus lambda I times the identity operator is not inject, that's actually what I have down right here. Let me erase that. But to be non-injective implies that lambda I is an eigenvalue. Okay, and so this has to be true because we can always factor the polynomial into this element. So we can always factor it into something that gives us factored into a collection of these operators from which we can show that you always have an eigenvalue. And so going back again to the proof, you see that the key thing is we took kind of a linear dependence, we made a polynomial, and we used the fundamental theorem of algebra. And key to use the fundamental theorem of algebra is that you have that the complex numbers, you're using the complex numbers. Okay, so I really want to highlight that existence depends upon your field f, right? Kind of as this little comic here is telling us, right? Because if we took the real numbers and we considered the linear operator given by 2 that takes the pair xy and sends it to negative yx, and if we apply the approach of the above proof with the vector v1, with the vector 1, 0, we would first get the vector v is 1, 0, tv is 0, 1, and t squared v is equal to negative 1, 0. Okay, so we have 3 vectors inside of R2, so they're linearly dependent, but it turns out in this case that the linear relation is 1 times the vector v plus 1 times t squared times v is equal to 0. So this would give us the polynomial pz equals to 1 plus z squared. Okay, so I'm just kind of following the proof, right? As what happens, I would take my particular vector, look at the linear, take powers. I would find a linear combination. It gives me a polynomial. And this is the part where it suddenly crashes. I can't go any further because I can't factor. So I can't go any further since the polynomial 1 plus z squared does not factor over R, right? So you can't use the fundamental theorem of algebra. So sometimes linear operators have eigenvalues, sometimes they don't, but if it's over the complex numbers, we always do have at least one eigenvalue. And it's a very slick proof because you're using kind of the fundamental theorem of algebra kind of hiding in the background. Okay, so just some key ideas from here today. I think like the big key idea here is this idea about polynomials related to operators. Okay, so that's going to be kind of a useful trick. And so we now know something also about the existence of operators. Okay, so just to kind of reiterate this first point, this trick here of taking a vector and then scaling up the operator and then getting a linear dependence, and which allows us to get a polynomial, is a trick that gets used from time to time in this course. Okay, so that's all I had to say for lecture 17. I hope you enjoyed it, and I'll see you in the next lecture. Have a great day.